Okay, we're going to be looking at problem 15 out of chapter 4, again, a method of joints. We have this really symmetric looking truss. We've got external loads, 20 kilonewtons here, 15 kilonewtons here, 15 here. We have a pin here, and I'm going to go ahead and model it like that. So we're going to call this R BV and R BH. And this is a roller. Over here it's C R CV. We have joint E, joint D, joint C, joint B, joint F, and joint A. So like any of these truss problems, we have to start out with reactions. So we're going to solve the reactions BH, BV, and CV. So I'm going to start out with the sum of forces in the X. Sum of forces in the X, we have R BH. And there is nothing resisting that, and so therefore this is a zero reaction. Sum of forces in the Y. In the Y we have RBV plus RCV minus 20 minus 15 and minus 15, and all of that is equal to 0. That's going to give us RBV plus RCV is equal to 50. So we're going to need to take a moment. Probably one of the reactions, knock out unknowns. We're going to call that clockwise moments. If I take it here, it'll knock out that one and these two guys. So that's probably a good place to do it. So I'm going to take moments at B. And starting with that 15 kilonewton, this is 4 across, 4 up, and these are 2 and 2. So that guy is at 2 over, 2 meters, 15 kilonewtons. That is tending to turn that counterclockwise. We also have this 15 clockwise, so this will be 4 plus 2. That gives me 6. So we have plus rotation, 6 meters, 15 kilonewtons. And then we have a reaction, so that's going to be a minus 4 or CV is equal to 0. So we're going to do this math here. We're going to find out that RCV is equal to a minus 60. We take and bring those guys over. Divided by a minus 4 gives us 15 kilonewtons. Positive indicates it's acting up the way we had indicated it initially. Plugging the 15 back into here comes over as a negative 15, and we wind up with RBV equal to 35 kilonewtons, also acting up positively. So what we want to do is replace these unknowns with knowns. And we didn't make any mistakes, so our orientation is correct. Even though this guy really doesn't have anything, I put it in there. It's just keeping track of everything. So we know that this one's 0. This one is B, that is RBV, that's 35. And RCV is 15. So now, as we analyze this, we look and we see that we are to solve BC, CE, and ED. And so there's different ways we could cut this, but the most logical place to cut it would be ED, CE and BC. So we're going to take a cut right through here. Now it's going to be kind of a weird looking cut, but it'll work out pretty nicely. Now again, you have two ways you could solve this. I could solve it on this side of the cut or this side of the cut. I would tend to go to the smaller side because I have less to deal with. So what I'm going to do is redraw this free body diagram right here, and we'll take a look at that. Okay, so we're looking at our section cut now, and looking on that little small section, and what we've got here are cut members here, one here, and one here. And I like to put everything in tension. I don't worry about which way it's acting. I know everything's not going to be tension, but that gives me CE, ED, and BC, which are the members that we need to solve. So we're going to go in and write equations. We've got 3 equations of equilibrium: sum of forces in X, sum of forces in Y, and sum of moments. So for sum of forces in X, we're going to have minus BC minus EDH has to equal 0. So don't get a whole lot out of that. See what we come up with for a sum of forces in the Y. So in the Y, we have 15 up, 15 down, CE plus ED vert is equal to 0. So what that tells us is that ED vert plus CE is 0. Okay, so that didn't do us any good. So what we're going to do now is do a moment equation. And again, you want to do it smart. If you take moments here, you lose BC and CE, but if you don't transmit this up to here, you're going to have a tough time solving this. So if we would take moments up here at E, it knocks out CE, ED, and it'll solve BC direct. So let's try that. Sum of moments at any point where clockwise is positive has to equal 0. We're going to go and take those at point E. And so that knocks this guy out. So we have this. This is 2 meters at 15 kilonewtons. That's a plus rotation. 2 meters, 15 kilonewtons. And this distance from here to here is 4 meters. So we're going to have a plus for BC, rotation equals 0. That gives us BC is equal to 30, comes over as a negative 30, divided by a positive 4, gives me a negative 7.5. So that tells me I'm not in tension, I'm in compression. And I can plug this guy back up into here. And when I do, that tells me that 7.5 minus EDH is equal to 0. Bringing those on the proper sides, I get 7.5 for EDH. And that tells me, since it's positive, that I did indicate that as a tension member, so that will be tension. So what we have now is a relationship. We can solve EDV, which will then solve CE for us. So what we're going to do is come here and say 7.5 is to 2, the distance over which it's acting horizontally, and 2 vertically, so it's 45, as EDV is to 2, and that resolves EDV into 7.5. Plugging that back up into here, we see that CE is equal to minus 7.5 when we complete that. And that shows me that CE is not in tension and some compression. So that's compression, that's compression. ED is a tension member, and that will be resolved by taking 7.5 squared, 7.5 squared, square root. ED turns out to be 10.6 kilonewtons in tension. So the trickiest part, this problem is probably recognizing where you want to take moments, and you can take moments more than once if you need to. Taking moments out here was great because it knocked these two guys out, solved this direct. If I would take moments here, I would have to take this guy up through transmissibility and get rid of the vertical component of ED and solve for the horizontal component of ED. So you have to think about that a little bit when you get into these types of problems. So hopefully that works well for you.